This video is about standard deviation, and it's intended for A-level biology students, although it could be used by anyone else wanting to know about standard deviation. And I want to do a fairly simple treatment, fairly basic treatment, because sometimes when you look at stuff about standard deviation and statistics on the internet, it can be a bit intimidating with all the terms and things used. So the first thing we want to look at is, why do we need standard? What's the use of standard deviation? Why bother with it? To do that, I want to show you some sample results. These are two classes in a school have taken the same test, which is out of 20, and these are their marks. Now let's have a look at class 1. Class 1, the marks don't vary an awful lot. The lowest is 12, the highest is 17, and an awful lot have got 14, 15 and 16. So they've done quite well, and they're much the same as each other really within the class. Class 2, the results are very different. They're much more spread out. You've got some people, one person's got full marks, 20, there's someone who's got 7 and done very badly on that test. So that is a completely different sort of class. It's a much more mixed ability class, and the performance is much more varied than in class 1. Now, sometimes when you have tests, those test scores are reported as means for the particular class. So the mean for class 1 is 14.25. Okay, fair enough. When you take the mean of class 2, that's 14.25 as well. And so anyone looking at just the mean might think, well, those two classes are pretty much exactly the same, but they're not. There is a great deal of difference because of the spread in class 2 compared with class 1. So the mean on its own doesn't really give you the full picture. And that's where standard deviation comes in. Standard deviation is a figure that gives you a measure of the variability, the variation in the results. Now, in these class results, if you look at the standard deviations, we'll work out how you get these numbers later on. But the standard deviation in class 1 is 1.48. As a number, that won't mean anything to you much at the moment. The standard deviation in class 2 is 3.29, which is more than twice as much. So immediately the scale of those numbers tells you that the variation in class 2 is much greater than in class 1. Now you might say, yeah, but why do I need a number? Why can't I just say class 1 got a mean of 14.25 and didn't vary very much, class 2 got a mean of 14.25 but there was a lot of variation? Well, standard deviation gives you a little bit more information than just how variable the results are, and we'll look at that in a minute. To understand it though, you need to know a little bit about what's called normal distributions. Normal distributions are this sort of distribution. What the distribution is that you get most of the individuals, most of the things you're measuring are clustered around the mean. They're sort of not too far away from the mean. So the value down here is what you're measuring. The frequency is how often you come across those measurements. Let's put the real situation here. This is the distribution of the heights of middle-aged males in the USA. And it shows that, in the sample they've used anyway, that these heights, the smallest one was about 5'1" and the tallest was about 6'5", and it follows this normal distribution, this sort of bell-shaped curve, right? That is typical of a normal distribution, and it's common sense really. Most people are not either extremely short or extremely tall. Most people are somewhere in the middle. Now let's have a look at the results from those two classes. This is class 1 and it does show a bell-shaped curve. It is a normal distribution. Class 2 is also roughly bell-shaped. I mean, you've only got 20 pupils, so that it's not really enough for statistics to be very accurate, but at least it gives an indication. Now, you notice that although they're both bell-shaped curves, the class 1 is much narrower at the base. Class 2 is much more spread out, and that's because of the variation. There's a much more bigger spread in class 2, so it spreads out the normal distribution. And the standard deviation is a formula that sort of is calculated in relation to the shape of this normal distribution curve. So we need to look at exactly where that comes from. If you have a mean, if you go one standard deviation below the mean and one standard deviation above the mean, you cover around about 68% of the data that you've got. So the standard deviation is calculated so that it represents one standard deviation either side represents 68%-ish of the data. If you go two standard deviations either side, then you actually take in 95.4, but roughly 95% of the population will be within two standard deviations either side of the mean. Now, so alright, how does that help us with these class results? Let's take class 1. Standard deviation is 1.48. Two standard deviations therefore is 2.96, and because of the way standard deviation is worked out, I know that 95% of the class will be between 2.96 marks less than the mean and up to 2.96 marks more than the mean. Now that works out as 11.29 and 17.21, but you can't have a mark of 11.29 out of 20. So let's say 95% of the class are going to be between 11 and 17 marks. Okay. Now, the other class, 3.29 the standard deviation, twice the standard deviation is 6.58. So in that class, I now know I can work out from the standard deviation that 95% of the class have marks between 8 and 20. Now, and that means that if I have the mean and the standard deviation, even if I haven't got the actual scores, I can get a much clearer idea of exactly what's happened in that class, about what the variation is. Now, there is something that is a little bit weird here, and that is that this mark here goes above 20. Now, quite clearly you can't have more than 20 out of 20, and the reason it does that is actually the normal distribution is not quite perfect. You sort of miss out this bit here of it. If you had a proper normal distribution, it would actually go to beyond 20 marks. That's probably because of the small sample, and we don't need to worry about it. You don't have to explain it or anything, but just in case you were wondering how anyone could possibly get more than 20 out of 20, they can't. Right, so the next thing is, how's it calculated? Well, you have a formula for standard deviation, or actually you have two formulae, depending on whether you're using a population or a sample. Now, in the ones we've used so far, the classes, we got data for every single pupil, all 20 in the class. So that is a population. We've not taken a sample of it. If we'd taken the marks for 10 of those 20 pupils in each case, we would have had a sample. And you can see that the formula is just slightly different. Down here is you've got n for the population and n minus 1 for the sample. You don't need to worry about that. Alright, so what do all these things mean? Well, S is simply the standard deviation. This is the a square root. You're probably familiar with that one. This one, sigma, means sum of all of them added together. X is the value of an individual reading. x bar, it's called, x with a little line on the top, that's the mean. Squared is squared, and n is the number of readings, or the number in the sample. Okay. So, alright then, how do you actually work this one out? Well, you do it this way. If you want to do it step by step. You first of all work out the mean. When you've worked out the mean, you've got x bar from that formula. Then you subtract the mean from the result, each result, and that gives you x minus x bar. Now some of those results will be negative, because in some cases the mean will be bigger than the result you've got. Then you square that answer, so that gives you x minus x bar squared. And that will get rid of the negatives, because a negative times a negative is a positive. Then you add up your answers to stage 3, because you will have got an answer for stage 3 for each reading. So that's the sum of x minus x bar squared. Then you divide your answer from number 4 by the number of results. That gives you sum of x minus x bar squared over n. And then lastly, to complete the formula, you take the square root of that answer. That gives you square root of the sum of x minus x bar squared over n. Okay. Now, often you don't have to do that, because the easiest way is scientific calculators have a sort of standard deviation button. Excel has a formula for standard deviation, so most people don't bother to do this sort of in the long drawn out stage, but that is how you would do it if you needed to. Right, just to finish off with, I want to show you one other example of how this can be useful. Now, farms are very important for the conservation of wildlife. They cover a large area of the country, and the particularly growing crops, because of herbicides and pesticides and things, there's not an awful lot of species of plant that live in a farmer's field, but they do live in the hedgerows around the outside if they've planted hedgerows, and so they are important areas for conserving plant and animal species. So supposing we wanted to see how well farms in a particular area are doing. So this is a fictitious study. We've taken these farms, a group of farms in a fictitious county, and we've worked out how many species of plant there are per farm on average. And the mean is 74. That sounds quite good. That's just the mean though. The standard deviation will influence what we think about these results a bit though. So let's take two possible examples. Let's suppose that when you work out the statistics, the standard deviation is 7.4. That means, remember, 95% will have a range somewhere between 2 standard deviations below the mean and 2 standard deviations above the mean. So that means 95% of the farms have got somewhere between 59 and 89 species. Now that looks, if I was in charge of conservation in rural Shire, I'd probably be quite happy with that. That's there's a bit of variation, but everyone's doing reasonably well. Now let's look at another scenario. In this case, the standard deviation is much bigger, 18.5. In that sort of scenario, although the mean is the same, I now know, because of the standard deviation, that 95% of the farms have got somewhere between 37 and 111 species. Now, that puts a completely different complexion on things, because if you've got 37, and of course a few will have less, if you've got 37 species, that doesn't sound very good, and especially compared to 111 or so. So what you might want to do, if you've got those results, is to say, well, okay, I need to look at those low farms and see whether they can learn something from the ones that have got over 100 species. And that's that adds extra information. That suggests that possibly some sort of intervention is necessary, whereas the lower standard deviation probably not. So the standard deviation can be a very useful thing in influencing your conclusions from the results. The other thing that it does do is, the bigger the standard deviation, the less confidence you can have that the mean is absolutely accurate. In fact, if you've got a large number of samples, it would be alright though. So standard deviation has these uses, and whenever scientists report a series of results, they will nearly always calculate and include the standard deviation for information.